Hello everybody and welcome to NPTEL online certification course on semiconductor devices for next generation field effect transistors, a physics perspective. This is lecture number 41 and the topic of the lecture is high frequency small signal modeling of FinFETs. So in our previous lecture we have introduced to you the FinFETs and then we looked into the structural classification of FinFET based on how you uh, possibly give biases to the system. So, we are an independent gate and we can have multiple gate, and then we are coming into a region where we will be discussing more of the high frequency modeling and typically small signal modeling. So, these two will be taken up, high frequency and small signal modeling. So, the outline for this lecture is I will explain to you the high frequency behavior of FinFETs and then discuss the Z parameter and Y parameters, the methods of extraction for FinFET, and then using a TCAD, standard TCAD, for example, Centaurus, how can you actually validate a FinFET model, right. So, that these three things or four things we will first try to explain to you. So, before we move forward and show to you how a FinFET looks like, two things I want to make it clear to you at this early stage of high frequency modeling, that in most of the cases when you study FinFETs and you say that it is a low frequency domain or high frequency, and you say it is a small signal or large signal, we need to be very cautious about what do you mean by high frequency and what do you mean by small signal, right. Now, relatively we define small signal as if the input voltage variation is approximately plus minus 10% of its quiescent value or of its mean value, then we define that to be as a small signal. From the point of view of modeling, so what we are saying is that if your quiescent signal is Q, then this plus minus 10%, which means that if your mean value is, let us suppose 1 volt, then if the swing input swing happens from 0.9 to 1.1 volts, then we can define this to be as approximately equals to a small signal. There is no direct definition, but this is how you can actually work it out from all practical purposes. Further, in small signal analysis, we assume that the linearity of the device is maintained, right. So, we also assume that the linearity of device, right, is maintained. So, you can understand. So, if it is a long one, then you will have a non-linearity, but if you keep it short, this will be almost like a straight line, and therefore, if any output characteristics shows a non-linearity in a particular region when you have large voltage variation, but that voltage variation almost becomes flattened or becomes a straight line when the input variation is made small. So, that is the reason we generally prefer to have sort of a high frequency behavior of FinFET, right. This is one thing. The second thing which I want you to take care of before we move forward is two things. One is known as the capacitive reactance and is given by 1 over j omega c, and we have inductive reactance which is given as j omega L, right, which means that at very high frequencies, when omega becomes very large, then Xc actually goes to 0 or the capacitor is shorted, right. When omega becomes very small, right, then Xc is almost increases and almost gap is open circuit. You can see it from this equation, right. Similarly, if we talk about j omega L inductive reactance, so this is your capacitive reactance and this is your inductive reactance. Then when the omega goes up, right, the XL value also goes up. This is proportional to each other, right. So, it then behaves like an open circuit, and when omega is reduced, XL reduces and then it behaves like a short circuit. So, this basic fundamental principle of a capacitance and an inductance should also be known to you a priori, right. Okay. Let me now come to the high frequency behavior of FinFET, right. We will come to this later on. Two things which you should be aware of, or you must be aware of, is that if we look at, let us say we are looking at FinFETs, right. So FinFETs are basically tri-gate. These are 3-gate devices, right. These are 3-gate devices and tri-gate devices, and you can also convert a tri-gate to a double gate by making the top layer oxide thickness pretty small. As you can see here, if you make this FinFET is there here only. So if you make this top gate oxide layer very thick, the gate loses control over the top gate, and a tri-gate converts to a double gate device. Where do we use this high frequency test cases? What are the test cases here? The test cases are basically 5G transceivers where we use it, right. And there we use FinFET for high frequency modeling especially, and then we look into uh, typically look into other devices, for example low power design, right, and so on and so forth. So typically your frequency of operation will be of the order of few gigahertz, that is defined as a high frequency model which we are predicting for a FinFET based design. Now uh, typically when you have, and I will come to this later on also, typically when you have multi fin structure, which means that rather than having a single fin, if you have multi fin, then you end up having a larger ion, right. So your performance actually becomes better. So if you look at the performance, it becomes better, but the cost you are paying for it is that your capacitance is also getting increased, and therefore the frequency of operation is getting reduced, right. And that is the basic problem statement which you face when you do a FinFET modeling, that there is always a give and take which happens. Uh, now what we are going to do in this lecture is multi-fin, and we will see how we can analyze the multi-fin structure using the Y parameter models. Now there are many models which are available. For example, BSIM IGFET models are available, and these are known as BSIM compact modeling group is there. This is a Berkeley short channel insulated, and this is basically the compact model group which works under that, right. And they have actually fabricated, have done quite a lot on the designing of these FinFET model files, which can be used directly by researchers in case of extracting the values of IV and CV characteristics. So one of the most common methods for extracting the parasitic effects are basically you need to employ what is known as a non quasi static model, NQS model, right. We do a non quasi static model using small signal modeling, and we do a multi-fin FinFET structure, right. We do all these things, right, and we are able to do this multi-fin structure coming into picture, which will increase the parasitic capacitances. Now if we are able to extract these parasitic capacitances using non quasi static model, we need to first of all understand what are the physical parameters, right. What are the physical parameters which actually influence the extraction or influence the capacitive loading. Now when you do a TCAD or a technology CAD sort of device modeling, then it is actually free from the effects of pad. So what will happen is that if you have this active device here, right, and it will be connected to external source pads, right. So there will be a pad here and there will be a pad here, and these will be a pad. So this will be VG, VD, say suppose VS, this is V source, right. So this is the intrinsic part of the device, and anything outside the intrinsic part is referred to as an extrinsic part. So as a designer, you need to do both of them together. You need to model both intrinsic as well as extrinsic part. To model intrinsic part, so we model the whole of it, and then we sort of remove the extrinsic part, and whatever is left is basically the intrinsic part modeling. And the intrinsic part, most of the parameters are either bias dependent or structural dependent of the FinFET. So why the capacitance model comes into picture is, when you give a bias, there will be always a charge modulation, right, charge modulation, and this will result in large value of variations in the output characteristics. Now, as I discussed with you earlier, and you must be aware of by this time, that these charges are basically geometry dependent. So typically, if the two fins are very close to each other, how does it influence? If they're relatively far from each other, how the fins are placed with respect to source and drain pad, and these influences the total capacitive model or the total charge collection model for the device itself. Now, what we do is, and what we will be going ahead is, that we will do a small signal modeling for Y parameter, generally which we people do for all high frequency models, and then using this we will try to find out the value of Ft and Fmax, the maximum frequency operation and transit frequency. These two we will be operating, and these are sort of a figure of merit, and typically the work done by our group here has actually extended the cutoff frequencies to approximately 50 gigahertz and beyond. So that I will come to you as we move ahead. Now let us look at the high frequency behavior of the FinFET and the modeling which is attached to it. So on the right hand side, you have this FinFET structure. This is your FinFET structure which I was talking about, right. So this is basically a raised source drain contact. So these contacts are raised source drain. This is your fin, and this is your gate here. Then there is a channel here, and there will be a flow. This is the height of the fin, obviously, and this is the thickness, width of the fin. So it is 2 H fin plus W fin as, let us suppose, the total width of the design, and this is the substrate which is available with us. Now if you look at the left hand side, which is this one, then the left hand side gives you the equivalent parasitic model of, or equivalent model of a short channel FinFET design, right. And if you look very carefully, the equivalent short circuit model has got many multiple capacitances and resistances in series and in parallel to the device structure, right. And let us see how it works out in that case. Now when we say NQS model or a non quasi static model, we effectively mean to say that that the underlying physics behind is that if you have a multi finger device and you are doing a non quasi static model, it primarily means that the frequency of operation is relatively very high. So keeping that in mind, let us go one by one and see how it works out. So this is a gate resistance, the resistance between the gate and the channel. This is the drain resistance, this is the source resistance. So these three resistances are sort of extrinsic resistances which do not necessarily be part of the device itself, right, and they are not exactly the part of the device, they are extrinsic to the nature. Next, let us look at this orange line. This is CGS1 and we have RGS. RGS is gate to source resistance, right. So gate to source resistance is basically the resistance between this point and this point, and it is in series to CGS1. CGS1 is gate to source capacitance, and there are two types of capacitance. One is an extrinsic capacitance and is an intrinsic capacitance. So CGS2 takes care of the extrinsic part and CGS1 takes care of the intrinsic part. This is on the source side. Similarly, between drain and source, you will have a drain to source resistance which will be parallel to the capacitance between source to drain. Now this GM times VGS is nothing but the current flowing through the fin. GM is del ID del VGS. So when you multiply that with VGS, you get the current available at that particular point, and these are the multi fin structures equivalent gate to drain capacitance and gate to drain resistances, right. This is gate to drain capacitance and gate to drain resistance. This is also gate to drain resistance, intrinsic and extrinsic in nature, right. Again, as a designer, you have with you H fin and W fin as the possible parameters which you can change as you move ahead. One is this one, Cm times VGS dVGS dt. This is basically a component which gives me the current flow because of the change in the signal at the gate side, right, and I am assuming this to be capacitance multiplied by the rate of change of gate voltage with respect to time. If you have large number of fins, if you have n number of fins, each fin will be represented. So each fin will be represented by a resistance, a capacitance and a parallel gap. So every time you encounter a fin, you can just plug this value here and you can move ahead. So that is what you get out of it. Now we will see later on that how the structural parameter depends mainly on the height of the fin as well as thickness of the fin, right. So this is very, very important. You should keep in mind that structural parameters of the FinFET do influence the capacitive elements of the device. Now uh, the total capacitance for each fin, the total gate to source capacitance, for example, gate to source capacitance and gate to drain is given by CGS1 plus CGS2 because they are in parallel, and CGD1 plus CGD2 are the total gate capacitances. RGD you multiply with that and you get the overall time constant tau value for at that particular point. Now let me come to how to extract it. So the extraction of the gate, source and drain resistance can be done by what is known as a cutoff method. What is a cutoff method? In cutoff method, VGS and VDS are given 0, which means that gate to source and drain to source are given 0. And once you get the 0, you get a distributed resistive network, and which can be therefore reframed by using a lumped network, right. And what people have done over a period of time is that what is known as a cold FET approach. In cold FET approach, we assume that there is no current flowing, therefore VDS equals to 0, but there is an inversion layer and therefore we assume that VGS is greater than VTH, right. So initially we extract the Y parameters from the TCAD throughout the all frequency range, and then from Y to Z we have a standard way of reconstructing the Z parameters if you are able to extract the Y parameters, right. Now as I told you earlier, your gate to source capacitance or gate to drain capacitances can be divided into intrinsic capacitances and extrinsic capacitances. Intrinsic capacitances are those capacitances which flow through the device itself, intrinsic capacitances, and extrinsic are outside the device. So what we are doing is that when VDS equals to 0 and therefore symmetricity is maintained, my gate to source extrinsic and gate to drain extrinsic capacitance is exactly equals to CE, which is the extrinsic capacitance. Why? Because when VDS equals to 0, the symmetricity of the device is maintained and therefore you will have this CGSE equals to CGDE equals to CE. Now for any two port network, you must be aware of this particular point, that Z external can be written by a 2 cross 2 matrix if there are two elements, and this is given by Z11, Z12, Z21 and then Z22, right. These we give, whereas Z11 is between this gate and source. So if you look very carefully, it is Z1 plus Z3, Z12 is Z3, Z21 is Z3 and Z22 is Z2 plus Z3, right. So what is Z1, Z2, Z3? Z1, Z2, Z3 are, this is Z1, this is Z2 and this whole network will be given as Z3, right. And this is how you perform the network. So the quantity Z11 and Z22 does contain Z3 as the common element, right, between the two element is common to them, right. So what we have done is that if you look carefully, Z1 is given by this RG. So this is series, right. This plus RDS divided by this quantity. So RDS is coming from here and Z2 is coming from RD. So looking from this side, the value of Z1 is known, looking from this side, value of Z2 is known, and Z3 is given by the source resistance, which is given by this Z3, right. So there are three components of impedance which is given by these formula, and if you look very carefully, the denominator is remaining the same for all the three cases, right, which means that the drain to source resistance plays an important role as well as the extrinsic capacitance also plays an important role. And if you therefore what you can do therefore is that you can actually have a frequency dependent resistance values, right, and from there I can extract for which frequency range what will be the total resistive value available to us. Now the same graph is repeated here and you can see here that I can convert that to a T network, and that is almost equivalent to a small signal parameter extraction graph here. So all the gate to drain network with multiple fins. So there are n fins available, and therefore we say that ZGDN is the effective capacitance or effective Z parameters impedance with n fin structure available. This is gate to source with n fin, and all other parameters remains exactly the same, right? And that gives me a interesting idea as far as this nature is concerned. Now the impact of extrinsic parameter is combined with intrinsic parameter to give you the overall effect. So you take the extrinsic, add with the intrinsic, and you get the overall effect. Now these are the values which you see, and this is the network which you see. So what I do is I get y overall is equal to z overall inverse, because y and z are inverse of each other, right? And therefore the two port network of a high frequency FinFET is given. We have already seen this point. This is ZGSN, right, which you see gate to source with n number of fins. This is ZGDN, which is gate to drain with n number of fins, and all other parameters have already been defined to you. So this is the y parameter modeling which you do in case of a z parameter. Now if you want to look at the overall y parameter small signal model, you need to just take care of this one. This has been calculated in the research paper, which is basically shown below here, our group's paper, and you can actually look into this paper to know the values of 1 by GSN and 1 by ZGDN, as well as 1 by C and 1 by D here, right. Now if you know the gate to source resistance and gate to source capacitance, then these can be calculated by doing a linear regression analysis from various frequency ranges, right, using various frequency ranges. This is the formula which we use, and if you plot therefore this graph and then you extend the graph, so y is equal to mx plus c, where it cuts the x axis, you will get the c value, right, and from there I extract that CGS2 prime is given by this quantity. Similarly, from that graph only I can calculate the value of RGD prime and CGD prime 1 value. These two can be easily calculated from that. Now one important parameter which you should be aware of is the transconductance of the device. The transconductance of the device is basically the difference between y21 and y12, the real part of it. If you look very carefully, the difference between them is nothing but the difference between the quasi-static model and the drain current which is flowing through the device. And this value of Cm is given by this quantity here, the imaginary value of y21 minus y12. Now the drain to source capacitance, if you want to calculate for omega equals to 0, I get the real part to be equals to this much. So once we know the y parameter y22 and y21, we extract the real part of it, inverse of that will be, or reciprocal of that will give you the value of RDS. Now, and these are the equations which I have already shown you in the previous slides, by which we can actually get the value of CDS. So now CDS is the drain to source capacitance which is there, including both extrinsic as well as intrinsic part. So once we have done this modeling, analytical model, and we have extracted the real and the imaginary part of all the y parameters, what we do is that we plot on the same axis real and imaginary part of y11 and y12, and then we plot the TCAD part. If you see very carefully here, let us see this TCAD. This is this black triangle sort of rectangle here. This is the TCAD, and the conventional model is given by some reference, and this is the modified model which you get for n is equal to 3, means this is basically a 3 fin structure. However, while imaginary part sort of matches very well, if you look at the real part of y11, you see there is a big deviation here, that the TCAD and the modified model matches very well beyond 100 gigahertz, but beyond 100 gigahertz, this green color, the conventional one, shows almost a flattened real value of y11. And the same is true if you look at this graph here, right. The same is true, that when you do a real part of y12, while the other values actually start to tend to change, this remains almost constant, which means that for the first time using TCAD and the model, we were able to match very clearly that beyond 100 gigahertz you can actually do a modeling for this FinFET, for Y parameter at least. The same thing is true when you do a Y parameter for the imaginary and real part using another model and with our model. As you can see here, if you look at this, particularly this one, you see the green part actually goes down like this, right, and the red dotted and the black rectangles, they move up together beyond 100 gigahertz, showing that it is well matched for n is equals to 3, right. So, this is a matching between TCAD, the conventional data, and the modified model. What we then did was we plotted the value of capacitance, the total capacitance, with the variation of frequency, and we saw that at higher frequency there is a dip in the capacitance expected also, because the capacitive reactance was actually getting reduced. And what we saw was the symbols are basically the TCAD, and the model is given by the line here for all the 3 graphs here. And the GM transconductance, as you can see, is actually falling down at high frequency values, which means that the rate of change of current with the gate voltage is very relatively goes small for high frequency, and it remains stable till 100 gigahertz. Till 100 gigahertz, the FinFET is able to give you a proper GM value, and that GM value is independent of frequency. Similarly, if you look at CGS and CGD, the black and the blue one respectively, they are initially constant and then shows a slight dip near the 1000 gigahertz range. Similarly, if you look at the second figure, there is a drastic fall in the value of CGG at high frequency, and we have plotted this with respect to temperature for higher values of temperature. The last figure is basically transconductance with respect to frequency, and that also shows a dip beyond 100 gigahertz. So, what we have found out was 100 gigahertz was sort of a benchmark or a leverage point across which the various values of capacitances and transconductance was changing, right. So, continuity is required at that particular point. This is again for a 3-fin structure, standard 3-fin structure. Then what we found out was that we are trying to find out the value of the transit frequency and the maximum frequency of operation. And we saw that if you look at the first graph, for example, the maximum frequency which we got of operation was 625 gigahertz, and this was done with the fact that the height of the fin divided by the distance between the 2 fins is approximately 1.05. So, height and the width were almost the same, and when you kept that, I got an F max of 625 gigahertz, and we got a transit frequency of approximately 427 gigahertz in this case, right. And quite interestingly, you will see that as H fin by S fin, the ratio of the height of the fin to the fin pitch goes on increasing or goes on decreasing. I can show you. Surely the frequency of operation starts to go down, right. And this can be true because when the height goes on increasing, or if the 2 fins go far away from each other, then there are other parasitic capacitances which come into role into play, right. And as a result, the frequencies tend to come down, and that is what you can see, that there is approximately some percentage drop in the value. This can be also attributed to a larger RGS value, because when your fin height increases, gate to source resistance also becomes larger. Okay. Now, what are the challenges? Basically, the challenges which you face with number of fin is, when you increase the number of fins, your gate resistance actually increases. So, though you gain in terms of a higher ion, but you end up having a larger delay because of the resistive effect of these gates, which is also visible to you for this. If you look very carefully at when the number of gates are 2 here, right, and also 2 here, the gate resistance is the minimum here. But as the number of fins then increases, the gate resistance also shows an increase beyond this particular point, right. Same thing happens for this case when you try to plot with the number of fins the gate resistance on the right hand side. This is for 2 different values of S fin. One is a 40 nanometer, another is a 42 nanometer H fin, and H fin by H fin ratios are this and this, right. And thus this gives you an idea that if you want to have a better control over the channel and you want to keep the resistance minimum, n is equals to 2 is the point where you should fix up the number of fins, or the number of fins should be fixed to around n is equal to 2. So, let me recapitulate of what we did in this lecture. we first looked into, we have already looked into the FinFET structure, but what we looked into was FinFET um, cap modeling, capacitive model, basic model. We looked into NQS model, and then we tried to extract the value of y parameters from z parameters, and from there we were able to achieve various values of y parameter and how y parameters are related to the resistive and capacitive elements in the device, right. And this gives you a brief idea that this is a methodology, one of the methodologies of basically FinFETs high frequency modeling can be done. So I hope you enjoyed this lecture, and please go through this research paper or other research papers which will give you a good idea about the RF modeling of FinFETs for those who are interested in this domain. Thanks a lot.